So the purpose of this video is to cover quickly a few key concepts about energy balance and also introduce the concept of enthalpy. So these are very central concepts for not just this course, but also several other courses that you're probably going to be taking in energy department in your studies. So this is why we are putting particular emphasis on this. And we're taking a look at this through an example. So here we have an open flow system in stationary state, and we have a couple of arrows going to and from. So first of all, because it's stationary state, what this means is because of first law conservation of energy, it means that all energy flows going in must equal all energy flows going out. And now we have a bunch of arrows going in and out, so those are the energy flows. We have two mass flows, one going in, number one, and then we have another one going out, number two. And with these mass flows, well, the mass is moving in and the mass has some state, pressure, volume, temperature. We remember from the Gibbs law that we need to know two state properties of a single pure substance so that the state is entirely set and we know what it is. So typically we know pressure and temperature there is the measure, and then that means that we can define everything else. And then we have W, that means work, and Q, that means heat. And we're some height Z at entrance and some different Z2 at the exit. Okay, so what's going in and what's going out? We have different types of energy. So we have the type of energy that is bound to matter. We have mechanical energy. We're familiar from high school physics that we've got kinetic energy, potential energy. The mass flow coming in has both, and the mass flow going out has also both. Then we've got internal energy, so that means the energy of the microscopic movement of the atoms or the molecules in the matter that is going in or out. So translation, rotation, vibration, they have microscopic kinetic energy. You can think of it that way. Then we have energy flows not bound to matter. So we've got work and heat. And work is, of course, any kind of mechanical work being done. And heat, important thing here is that it is not bound to matter. We're talking about heat transfer, so heat that is transferred through radiation, convection, conduction. No, if you have hot matter, it doesn't have heat, it has internal energy. So work and heat are only two ways how we can move energy in or out from the system without moving matter. And we always do work when we move mass into or out of from the system. There's always work done, of course, basic mechanics. If we have a shaft poking through the system boundary and we're rotating that shaft, then work is being done either by the system or into the system, depending on where the force to rotate the shaft is coming from. And if we are compressing matter, we are doing work. We call that PV work. So, okay, if we now write out a balance equation, so basically a balance equation just says that everything that goes in must equal everything that goes out. And we have now formulated this with not as work and heat, but power, which is work per unit time, and heat rate or thermal power. Of course, same concept, so heat per unit time. So we just write an equation that says that everything going in must equal everything going out. What goes in is this mass flow rate in times all the types of energy that the mass flow rate brings with it, plus the phi, Greek phi letter, with which we mark the heat rate. And what goes out? Everything that mass flow rate 2 brings with it, plus the power which is going out from the system boundary. Now let's take a look what we have here. So we have the same components just for state 1, state 2. We've got specific internal energy. We've got the flow work. We've got the kinetic energy and potential energy. So velocity squared divided by 2 familiar equation for kinetic energy, same thing for the potential energy, same for both sides. And now, when we look at this, for example, this lowercase u, now that's a state variable, specific internal energy. So once we know pressure and temperature, we can look up from the table or look at the chart, see what value that will take as a function of the two other state variables. Okay, the mechanical ones are pretty straightforward. We know that from high school physics. Now let's take a look at the flow work. So there's this PV term on both sides. So basically, as we said, every time we have mass crossing the system boundary, flow work is being done. Now the question is how much work is being done, and the answer is that we imagine a tiny little bit of matter right at the border when it's about to enter the system. So we imagine it as a tiny little short distance s, that is the length of the unit mass. And to move it in, we must do work. Work is force times distance. Distance is this short length s. So whatever force it is that pushes this amount of mass through the distance s, which is what it takes to enter the system. The question is, what is this force F? Well, if we've got some kind of pipe or tube or whatever, and there is gas or some other fluid flowing through, water maybe, so we're talking about power plant engineering here, so we're talking about different kinds of fluids. Well, the only thing that can push it in is going to be the pressure acting on that unit of mass. So if the pipe has certain area, frontal area A, the force that the pressure P causes is pressure times area. And then we have the work that is being done as pressure times frontal area of the tube times the distance S. Now we have here area times distance. That is volume, so work is PV, pressure times volume. And if we have a continuous mass flow rate, then we don't have energy and joules, but we have the mass flow rate times PV, and we've got power with a unit of watt. Okay, now every time we put this matter in, we have to do this flow work. And the amount of flow work that we are doing is a function of pressure and specific volume. And just like the internal energy, which we have on both sides, pressure and specific volume are also state variables. That means that once we know, for example, the temperature and pressure or any other two state variables, also P and V are completely fixed. So just out of convenience, we are combining these two because they are always together in the balance equation. We say that specific internal energy plus P times V, that is enthalpy. And we just simplify our equation this way a little bit. And as usual, enthalpy, capital H, that is the extensive property, and the intensive property is made by dividing it with the amount of mass, and we mark that with the lowercase letters. Now, okay, this way our equation becomes a little bit nicer, but we can still simplify it quite a bit more so that it becomes maybe a little bit more practical for everyday power plant engineering calculations. So let's do that. We can introduce a concept called total enthalpy, which also includes the specific kinetic energy of the flow. So we mark with h tot, and specific kinetic energy is half of velocity squared. And very often we can also say that potential energy change can be assumed negligible. This is because we're talking about thermodynamic cycles, power plant cycles, power cycles. So cycle means that you start from one point, you end up right back at it, even if you're the height from any zero level that we may define varies even quite a bit. In the end, it all balances. So we can say for purposes of calculation that potential energy change is negligible. And then this starts to look quite a bit simpler. So now we have just mass flow rate times the enthalpy it brings plus heat rate, and same thing on the other side. And now because the arrows are going this way, we have the power as the leaving energy. But I highly recommend that always just draw the picture, mark all the arrows, what is going in, what is going out. If it's a pump, the power is going in because you need external power source to run the pump. If it's a turbine, the turbine is producing power. It's turning the shaft that turns the generator, so the power arrow is going out like we have it here. And within this course, when we talk about enthalpy, we basically always mean the total enthalpy unless it's explicitly stated otherwise, and I don't think it ever will be stated otherwise. So basically, it's simple enough concept to understand from the perspective that if there is some very high velocity flow, for example, very high velocity, so this term becomes significant. If we actually measure the temperature, we are not going to get a reading for the static temperature, which would be the reading that we got from an imaginary temperature sensor that was floating with the flow and going at the same velocity. We're going to get a temperature reading that includes what happens at the surface of our temperature sensor. So what happens at the surface of the temperature sensor? The flow velocity exactly at the surface is actually zero. It means that all the kinetic energy of the flow at that point was converted to something else, and what the something else is specific internal energy. And that means that temperature has increased, and that means that this is the reading that we're actually going to get. So once you go to more advanced courses about turbines, for example, then it becomes important to differentiate between static and total states. But within this course, we're always talking about total state, and we don't have to care about the velocity because we assume that it's always baked in to the temperature reading that we are getting at whatever point we are measuring.